objects is a very common and important occurrence. Is it possible to describe that motion in a simple yet scientific way? The answer is yes. One branch of physics, called kinematics, deals with how objects move and the description of that motion with relatively simple equations. We begin by considering which physical quantities are actually involved in motion. The fundamental quantities that are important in describing motion are position, displacement, time, velocity, and acceleration. Most of these quantities are vectors. A vector is a quantity that has both size and direction. In order to find the position of an object in one dimension, it is necessary to have an appropriate frame of reference. Imagine a long line with a reference point in the middle. The directions along the line to either side of the reference point can be thought of as being either positive or negative. Finally, appropriate units are chosen for measuring distances. The SI units of length are meters. Now, the location of any object can be completely described with a position vector. We use the variable x to describe position. So, this object would have a position vector of x equals positive 3 meters. What is the position of this object? Correct. A position vector should have a direction, distance, and units. So, x equals negative 2 meters. When an object moves, its position changes. The quantity that represents change in position is called displacement. To find an object's displacement, it is only necessary to know its beginning and ending positions. Displacement is represented by the variable delta x and is equal to the difference in the final and initial positions. Here we see an object with a displacement of positive 3 meters. What is the displacement of this object? Correct. Displacement is equal to final minus initial position. So, delta x equals negative 3 minus positive 1, or negative 4 meters. Time is another important quantity used to describe motion. We can refer to a specific time t at which an object is at a particular point. We can also refer to a time interval delta t over which an event occurs, such as the motion of an object. Delta t is equal to the final time minus the initial time. One of the most basic questions that we can ask about an object in motion is how fast is it moving? The answer is the object's speed, or velocity. The average velocity of an object is a vector quantity that depends on when and where the object begins and ends its motion. It is defined as the displacement divided by the time and is represented by the variable v bar. The magnitude of the velocity is called speed, and the direction is the direction of the displacement. For example, if a car travels 40 meters in the positive direction over a time period of 8 seconds, its average velocity would be positive 5 meters per second. So, if it takes you 4 seconds to travel 10 meters in the negative direction, what is your average velocity? Correct. Negative 10 meters divided by 4 seconds gives an average velocity of negative 2.5 meters per second. We have talked about average velocity, but there is also what is known as instantaneous velocity. Instantaneous velocity is the actual velocity of an object at a given instant in time. The motion of an object can be studied with a graph of its position as a function of time. On such a position-time graph, the average velocity of the object is equal to the slope of the line connecting the 2 points at the start and end of the time period during which the object moves. The instantaneous velocity of the object is equal to the slope of the line tangent to the given point. When an object's velocity changes as it speeds up, slows down, or turns, it experiences acceleration. The average acceleration of an object depends only on its starting and ending velocity and the time interval over which it changes. Average acceleration, or A bar, is equal to the change in velocity divided by the change in time. Instantaneous acceleration is the actual acceleration of an object at a given instant in time. On a velocity time graph, the average acceleration of the object is equal to the slope of the line connecting the 2 points at the start and end of the time period during which the object moves. The instantaneous acceleration of the object is equal to the slope of the line tangent to the given point. If the graph of velocity versus time is a straight line with a positive slope, is the acceleration zero, constant, or increasing? Correct. The acceleration is equal to the slope of the line, which remains constant. When motion is in one dimension and the velocity is constant, a simple set of equations describe the motion completely. An object's position as a function of time is equal to its starting position plus its starting velocity multiplied by time. Its velocity remains constant over time. When motion is in one dimension and the acceleration is constant, another set of equations can be derived to describe the object's motion. An object's velocity as a function of time is equal to its starting velocity plus its acceleration multiplied by time. Position is equal to the initial position plus the initial velocity multiplied by time plus 1/2 the acceleration multiplied by the time squared. The third equation is derived from the first two by eliminating time as a variable and relates velocity, acceleration, and displacement. These equations of motion can be used to solve a variety of problems. Consider a car that has an initial velocity of positive 5 meters per second. It accelerates at a rate of positive 3 meters per second squared for 6 seconds. How can we analyze this motion? The best way to start any problem is by drawing a diagram of the motion. Then identify what information is given and what needs to be found. What is the car's final position? Correct. Substituting the given values into the second equation and simplifying gives a final position of positive 84 meters. A common example of one-dimensional motion is free fall. An object in free fall has an acceleration equal that of gravity, that is, an acceleration equal to that of an object that is dropped and falls straight towards the Earth. The acceleration due to gravity near the surface of the Earth is about 9.8 meters per second squared. When dealing with objects in free fall that are moving vertically, it is customary to use y rather than x to represent their position. Also, the acceleration a is replaced with negative g, since the acceleration will be down or negative in direction and equal to g in magnitude. Think for a moment about objects in free fall. Aristotle claimed that the acceleration of a falling object depends on its mass, or in other words, that heavier objects fall faster. Galileo disagreed, saying that the acceleration of a falling object is independent of its mass. Who do you think was correct? Let's find out by dropping two objects with different masses from the same height. According to Aristotle, the heavier object should hit the ground first. Galileo would say that the two objects should hit at the same time. Galileo was correct. The speed of a falling object is independent of mass. It is possible to use the equations of motion for an object in free fall to experimentally determine the acceleration due to gravity. Suppose an object falls from an initial height of positive 1.25 meters to the ground, a height of 0. If this free fall takes 0.505 seconds, then what is the object's acceleration? Correct. Substituting the given values and solving for acceleration gives the predicted value of negative 9.8 meters per second squared. So, as you have seen, it is possible to describe motion in one dimension with a constant acceleration in a simple yet scientific way using these fundamental equations. A ball is dropped from a height of h. Use the simulation and analytical calculations to determine the value of h. Use the simulation by setting the initial velocity v0 that the ball will be thrown downward at. The timer will begin as soon as the ball is released and will stop once the ball has landed. Use the time and the initial velocity of the ball to determine the height h. Input a value for v0 and click on the Run Simulation button. Good job! Your answer is correct. Click on the Solution tab to review the calculations, or click on the Exit Sim button to move on in the lecture.